स्टार्ट कर दइए। करिए स्टार्ट। आवाज आ रही है मेरी? ओके। आवाज नहीं आ रही।
A lovely morning to all of you. I am Dr. Aksh Sharma, your host for today's session. On behalf of University Institution of Sciences, who has clubbed all of us for the national seminar, I welcome our honorable resource persons, Dr. Ranjit Singh and Ms. Jyoti. I extend cordial welcome to our worthy Vice Chancellor, Sir Dr. Dharamveer Singh Parmar, worthy Registrar Ma'am, Dr. Ilu Sharma, Dean UIS, Dr. Shweta Singh, Deputy Dean UIS, Dr. Nisha Sharma. Under the heavenly blessings of Sant Baba Dilawar Singh Ji Brahmji, under the chief patronage of Chancellor Sant Sarwan Singh Ji, and under the able guidance of worthy Vice Chancellor Sir Dr. Dharamveer Singh Parmar, University Institute of Sciences, under the aegis of IQAC, has organized a one-day national seminar on the topic Effects and Consequences of Radiations in Current Scenario through Online Mode. University Institute SBPSU has been established in 2015 with a vision to encourage each and every child to get educated, acquire knowledge and wisdom, so as to learn the art of leading a happy, successful, and meaningful life. The University Institute of Sciences has been actively engaged in the all-round formation of the future scientists, scholars, and professionals since its inception as a part of Sankava Bhag's UIS is blessed with well-qualified faculty with research interests in diverse fields. The national seminar of today, it comprises of two lectures by two resource persons, Dr. Ranjit Singh, medical physicist, PGI Chandigarh, and Ms. Jyoti, HOD Radiology and Imaging Technology, Sushant University, Gurugram. It is a moment of great pleasure that we'll all be connected to and be able to interact with such elite personalities. So first and foremost, we move towards our inaugural session. I would like to request our Vadi Registrar Ma'am Dr. Indu Sharma to please grace this session and say a few words about the seminar.
A very good morning to all the participants. If I'm audible to you,
Yes, ma'am.
please let me know if I'm audible to you. Okay. Thank you
Yes,
so much
yes.
for inviting me and for the opening of this seminar. So, if I talk about the seminar, this topic is highly relevant for the day because we encounter a number of type of
Ma'am, we
radiation.
are not audible.
I'm not audible.
Excuse me, ma'am.
Okay. So, I'm audible now? Ma'am, kindly let me know क्या मैं audible?
Yes, ma'am, you are audible.
Yes, ma'am. Yes,
Okay.
ma'am.
So if we talk
Yes,
about the
ma'am.
radiation, we encounter different kind of the radiations on the daily basis. But among all the radiations, the most harmful radiations are one of the high energy radiations, which involve radioactive radiations, X-rays, UV rays, etc. And these radiations basically influence the habitability as well as they play a crucial role in the abiogenesis. These radiations, they impact our day-to-day life, and major nuclear radiations which have been released during the Chernobyl disaster are also a living example for us that they have changed the planetary atmosphere. So this topic, which we have chose today, that is National Seminar on Effects and Consequences of Radiations in Current Scenario, is quite apt to discuss that what is the impact of the radiations, whether all the radiations are harmful to us, and if radiations are harmful, then which type or what type of radiations they are harmful to us. So this workshop or this seminar is of quite interest, and I hope that this seminar will be beneficial to each and every participant to understand that how these radiations they impact our life. I wish a very good luck to the conveners, Dean UIS and Deputy Dean UIS, as well as the organizing committee, including Mr. Rajdeep and Dr. Harpreet, all the members who are involved in the organization of this seminar. And I really welcome the speakers, the resource persons. We have today with us Dr. Ranjit Singh, who is medical physicist from PGIMR Chandigarh, and Ms. Jyoti, who is the head of the department, Radiology and Imaging Technology, Sushant University, Gurugram. So welcome to university, and on the behalf of university, I really appreciate that you have given your time for guiding our students, and thank you so much. And I wish good luck for the seminar. Thank you so much.
Thank you so much, ma'am.
Thank you, ma'am. Your words are always a source of motivation for all of us. Now, without taking much of your time, I would like to hand over to Dr. Harpreet Singh to introduce and welcome our first keynote speaker, Dr. Ranjit Singh. Over to Dr. Harpreet Singh.
Good morning to everyone. It is my pleasure to invite Dr. Ranjit Singh, who will lecture based on the radiation physics. First of all, I will discuss about little bit about Ranjit Singh. Dr. Ranjit Singh is working as medical physicist since 2010 in the Department of Radiation. He did his MSc in physics from United University in 2006 and did his post-MSc diploma in radiology physics from Baba Atomic Nuclear Research Center in 2019. After completed his diploma, he engaged in PhD from Punjab University, Chandigarh. He is a lifetime member of Association of Medical Physics of India. Apart from it, he has published more than 25 research papers in reputed international journals and published 2 international book chapters. More than 10 students did an internship in medical physics under his supervision. Despite daily discharge of his duties, he is now actively involved in different academics and teaching radiology physics for BSc, MSc, and MD classes. His area of interest is volumetric art therapy, image-guided therapy, and patient in vivo dosimetry studies. Ranjit Singh to deliver a talk on radiation protection and dosimetry in medicine. Now we will invite Dr. Ranjit Singh to present his presentation. Dr. Ranjit Singh. Dr. J.C., you will, Dr. J.C. लगे कर
Your voice is not audible.
हाँ जी सर Yes, sir, 31. I do lot of them.
chemical waste and chemical related waste and radioactive waste.
Good morning, everybody. Myself, Dr. Ranjit Singh. I am working as a medical physicist in the Department of Radiotherapy, PGI Chandigarh. First of all, I am very thankful to the worthy Vice Chancellor, Registrar Ma'am, Dean, all faculty members. Is it audible to everybody?
Yes, sir.
Sir, yes, sir. You are audible, sir. Please.
I am also thankful to all faculty members of the University of Sciences, Sant Baba Bhag Singh University, Jalandhar, for giving me a chance to participate as a resource person for national seminar on effect and consequences of radiation in current scenario. My today's topic is on radiation protection and dosimetry. As you know, there are two types of ionizing radiation: charged particles, for example, alpha particles, beta particle, and heavy ions. There are uncharged particles, for example, X-rays, gamma rays, and neutrons. These all radiations, they are contributing in different scenarios in medical physics. Now, the application of radiation in medicine. As I told you earlier, they have used in different scenarios, but at the side, these radiations with different energies, they are being used in diagnostic as well as therapy. In diagnostic, we make use of X-ray imaging, where the energy of X-rays are of the order of kilo-electron volt. Then we have that computed tomography. We make use of that also in order to diagnose, to get the proper diagnosis of the patient. Then there are distal subsection angiography. That is also technique that use X-rays, and that is very much useful in the brain studies as well as in the cardiovascular disease. Then we have the positron emission tomography that make use of F18, carbon 11, gallium 68. Half-life of this F18 is 109 minutes. That of the gallium is 60 minutes, and C11 has a half-life of 20 minutes. So all these radionuclide, they are used in positron emission tomography, and that is came in the nuclear medicine department. Then we have the gamma camera that make use of technetium 99M and also iodine 123 with the help of different radiopharmaceuticals for different type of investigations, including different organ at interest. So we have a thyroid also, thyroid update probe that is used for diagnose thyroid cancer, that make use of iridium 123. The half-life of iridium 123 is 13 hours. In spite of radiation being used as in diagnosis, it is also useful in therapy. In therapy, we use external beam radiotherapy, where X-rays of high energy of the order of mega electron volts, X-rays, gamma rays, beta particles, heavy energy or high energy beta particles, heavy ions, for example, we have proton therapy, so that make use to treat the cancer patients or cancer cell. Then this is the actually in the radiotherapy we have another branch which is called brachytherapy, which is also known as short distance therapy, and that make use of different sources. For example, cesium 137 with a half life of 30 years, cobalt 60 with a half life of 5.26 years, radium 192 with a half life of 73.8 days. They all are used as sources in brachytherapy. Brachytherapy is the branch where either the source is very close to the target volume, or it is surgically placed inside the tumor with the help of needles, plastic needles, or stainless steel needles. Then this brachytherapy is further advanced into endovascular disease. There is a cardiac disease where there is a stenosis. Stenosis is nothing; it is a blockage in the arteries of the heart, and but that blockage will be re-stenosis after some time. So, but if you are making use of different sources, then this chances of re-stenosis means accumulation of further narrowing of the arteries that will be reduced. Then brachytherapy is also used for eye plaque brachytherapy. In case of eye plaque brachytherapy, the most common tumors for eyes are the retinoblastoma and uveal melanoma. So in that case, if that is very aggressive or that will be in grade 4 stage, then in that case, the eyes of that patient will be removed. But if it is in the low grade tumors, then we can make use of proper use of this brachytherapy sources. We implant that in the eyes to treat the patient which is of retinoblastoma or uveal melanoma. Then there is a rhenium source therapy that is used for the treatment of moles. These moles are benign. It means that will not grow in an uncontrolled fashion as compared to that of the other tumors. That will be remain in the body. That will not. Sometimes it will not harm to the concerned individual. But even then, we are making use of this rhenium source therapy to treat that mole. And in this case, we are making use of rhenium 188 source with a half-life of 6 hours. Then we have a radioactive iodine therapy that is used for the treatment of cancer patient. And in this case, we are making use of iridium, the iodine 131 source. These are the different sources that we are using in brachytherapy. We have radium 226, cobalt 60, cesium 137, iridium 192, gold 198, iodine 125, palladium 103. So nowadays we are not using radium 226. This is because of the reason that the sources we are getting, they are doubly encapsulated. But the disintegration daughter product of radium 226 is the radon 222, and that is a gaseous in nature. So that will create pressure inside the encapsulation, and there may be chances of leakage of the radiation, okay, spilling of the radioactive material. So that's why it is not used. And other thing is it is of high energy. If you see the photon energy, it is the maximum photon energy is 2.45 MeV. So,
Excuse me, sir. Excuse me, sir. Sir, can you change the slide? We are not seeing your slide. So we have only seen your front side. Can you change a little bit? So there is a next option here from your keyboard. You can change the slide from your keyboard. Yes, sir. Yes, sir. Yes, sir.
Okay, but I think it is smaller, little smaller in size. Is it?
Yeah, it we can see here. No problem, sir.
Okay.
Yes.
So that's why radium 226 is not used nowadays. And other major disadvantage of using this radium 226 is that it is its specific activity. Specific activity is nothing but it is the activity per unit mass of that material or radioactive material. So that specific activity is very low, as a result of which sources, if we want to give the desired dose to the target volume, we need sources of large size. If there is a sources of large size, then the applicator size, that applicator that will go inside the patient body, that will be also of larger size, and that will result in greater patient discomfort. Okay. Next is the effect of radiations. So there are deterministic effect of radiation and stochastic effect of radiation. So deterministic effects, they are from the acute exposure because of the cell killing. There is a threshold value for the dose. For example, if we consider LD 5060, LD 5060 is it is nothing but it is the lethal dose which expose the given population. 50% of the population will die in 60 days, and the value is 3 to 5 gray. If 3 to 5 gray is the dose delivered to a population, to a given population, then 50% of the population will die in next 16 days. Okay. So this dose is this absorbed dose is nothing but it is the energy deposit per unit mass of the material. Okay.
Okay.
So next, its severity of the deterministic effect increases with the increase in threshold dose value. There is a stochastic effect. There is no threshold value for the stochastic effect. Chronic and acute exposure both are responsible for stochastic effect. One of the example of stochastic effect is the cancer induction. Next is the latent period. They have a certain latent period, mean to say that the individual exposed, that is the time between gap between exposed time of exposure and that of the occurrence of the cancer, that is called the latent period of. For example, if we consider the case of atomic bomb survivor from Hiroshima and Nagasaki, we found that the latent period, the most of the tumors in the first decade will be the blood cancer.
Okay.
Then in the next 30 years, the latent period of the bone, the solid tumors, bone cancer, they will have a latent period of 30 days. Next is the principle of radiation protection. So there are three principles of radiation protection: optimization and limitation. Before you're going to start making use of the radiation, you must be properly justified that you can derive the maximum benefit from the minimum risk. Or in other word, you can say the benefit should be greater than the risk. You have to. Then next is the optimization. So with make best possible work scenario, you can further reduce the dose. Then there is a dose limitation. So every radiation worker, they are provided with the dose limitations, and that will be assessed every quarter in a year, so that we can monitor that dose to the radiation worker should not exceed the dose prescribed by the competent authority. So competent authority in PGI and in India is the Atomic Energy Regulatory Board, which is situated in BRC, Bhabha Atomic Research Center, Mumbai. Next is the radiation quantities. So first is the absorbed dose, that is defined for all type of radiation. That is nothing but this is the energy imparted per unit mass of the medium. Its SI unit is gray, and CGS unit is rad, and 1 gray is equal to 100 rad. Then second is the gamma, that is also defined for all type of radiation. That is nothing but this is the sum of the kinetic energy of charged particle liberated from the interaction of radiation per unit mass of that medium. The unit is again same, that is gray, and CGS unit is red. Then we have an exposure. This is the oldest unit. that is defined for X-ray and gamma radiation only, and medium should be air. Energy should be less than 3 MeV, and its unit is Roentgen, and 1 Roentgen is 2.58 into 10 raised to power -4 coulombs per kg. Then certain other radiological units are dose equivalent. We know that the radiation, different type of radiation, they have different impact on the medium, they have different interaction in the medium, they have different penetration in the medium. So different radiation, they are assigned different value, and this dose equivalent is equal to absorbed dose into radiation weighting factor. Its SI unit is sievert, CGS unit is RAM. These are the radiation weighting factor for photon and electron. We have 1 because the photon also interact in the similar fashion to that of the electron, because that electrons liberated from interaction of the photon with the material, they will further dissipate the energy. So that will be photon and electron both have given same radiation factor. Then we have the for proton and charged particle, radiation weighting factor is 2. For alpha particle, fission fragments and heavy ions, it's 20. And for neutron, since this neutron will have different absorption cross section to a given medium, depending upon their different energy. So that's why a continuous curve depending upon the energy, the radiation weighting factor is assigned to neutron. Then we have effective equivalent, effective dose equivalent. Now we have considered that we know that the effect of the radiation will depend upon the ionizing radiation. It also depends upon the tissues, the sensitivity of different tissues. Some of the tissues or some of the organs, they are very sensitive to ionizing radiation, and others they are less sensitive to ionizing radiations. So there are further this effective dose. It is the sum of weightage of the equivalent dose for the organ, and then we have to multiply this with the weighting factor, tissue weighting factor. So different tissues, they are assigned different values, which is the tissue weighting factor. For example, bone marrow, colon, lung, stomach, breast, and remainder tissues. Remainder tissues are nothing but it is adenal, extrathoracic region, gallbladder, heart, kidney, lymphatic nodes, muscles, oral mucosa, pancreas, prostate, small intestine, spleen, and thymus, and the uterus or cervix. Then for gonads, its radiation weighting factor 0.08. That this radiation weighting factor will be assigned according to the their interaction with the radiation. Then for bladder, esophagus, liver, and thyroid, the assigned value is 0.04. For bone surface, brain, salivary gland, and skin, the value of tissue weighting factor is 0.01. So in spite of medical exposures, there is background radiations which continuously bombarding the atmosphere, and it is also bombarding the each individual living on the earth. So the terrestrial radiation that also depend upon the that will vary from region to region. For example, if you consider the beaches which are in Kerala, you will find activity of the annual dose accumulated to the individual residing there is of the 9 to sievert. Although the average value of background radiation is 2.5 to 3 millisievert in rest of the part. Then the cosmic radiation that comes from the outer cosmos, outer atmosphere, that is also continuously bombarding our Earth atmosphere. Then there is the presence of radioactive element in our body, K40, whose half-life is 1.3 into 10 raised to 9 here. So means if a person turns into ashes, even then this K40 is present in the ash of that person. So that is also continuously bombarding the body of the individual. So this is the average value that we have got. It is of the order of 2.5 to 3 millisievert per year. Then next is the effective dose equivalent. So then the third step that I have explained you earlier in the case of radiation protection is the dose limitation. So there are certain dose limits for general public as well as the radiation worker, and also for the trainee who are working in the radiation zone areas. Okay, those who are doing their BScs, MScs in the radiotherapy department or in the other department also. For example, nuclear medicine department, then diagnostic department. So they have certain dose limit are being assigned to them, and that those limits are assigned keeping in mind that at this low level of radiations, stochastic effects are negligible. Means the chances of cancer induction is negligible. Okay. Then second is the risk associated with the radiation industry and that of the other industry should be also verified. So this is the NCRP report 86, which is published by the American Association of Medical Physicists. So according to that, we have got that for safe industries, for example, transport industries, then teaching sector, all these, the annual fatality rate is 10 person per 10 lakh. But in the radiation industries, 3 person will be die every year with the radiation out of 10 lakh. So we can consider that, we can say that radiation industry is the safest industry. And further, we can reduce the dose limit if our work practice is good. This is because I give you an example for this. For the imaging, X-ray imaging of different part, we know that different part they have different thickness. For example, for neck, thickness is slightly less as compared to the abdomen or pelvic region. So with the best possible of filament current, applied voltage, and the MAS, which is the product of current and the time of exposure, that should be kept in such a way that the lesser doses will be received with the maximum information drawn from the X-ray imaging. So further, if your work practice is good, you can achieve the principle of ELARA, that is as low as reasonably achievable. Okay. So next is the dose limit. For radiation worker, whole body effective dose is 20 millisievert, average over defined period of 5 years with not more than 15 millisievert per year in a single year. For trainee, it is 6 millisievert per year, and for general public, it is 1 millisievert per year. But in this is actually these are the limits that is given by International Atomic Agency, IAEA, Energy Agency. But in India, this is further modified by the ARB, which is the competent authority of in India, and they have said that 20 millisievert average over a defined period of 5 years with not more than 30 millisievert in a single year. So they have reduced to 30 millisievert per year.
Excuse me, sir. Sir, you have discussed about the dose limit. Is this a standard value? Is this standard value for all over the world, or for only for India?
Actually, whatever dose limits they are shown to you, that is given by the IAEA, that is the International Atomic Energy Agency. But in India, ARB, who is the competent authority, they have further modified it. Okay. If you see here, for whole body, there is the limit is 20 millisievert per year, average over 5 years. But in single year of 5-year calendar, you should not receive 50 millisievert as far as ARB, as far as IAEA. But as for AERB, it should not more than 30 millisievert per year. Okay.
Thank you,
So-
sir. Thank you, sir. Okay.
Then for different parts, for example, lens, these are the values: 150 millisievert per year for radiation worker, 50 millisievert for trainee or apprentice. For public, it is 15 millisievert per year. For skin, it is 500 millisievert per year for radiation worker, 150 millisievert for trainee, 50 millisievert for public. Similarly, is for the hand and feet. So next is the dose limit to pregnant radiation worker. So that effective dose she will not receive more than 2 millisievert per year on the abdomen, so that the fetus which has baby which come in the as a general public should not receive greater than 1 millisievert per year. Okay. And these are the dose limit when you find that the patient is not comfortable and additional help in the form of relative is required inside the diagnostic room or treatment room, then this is the 5 millisievert per episode, and for visitor it is 1 millisievert per year. Then radiation monitoring instrument. So we have this ionization chamber. Then we have GM counter, GM survey meter. For personal dosimeters, we have this TLD batches, film batch, and pocket dosimeter. So out of this personal dosimeter, TLD batch and film, they are passive dosimeters that will not give you reading at a given instant, but for that certain procedure has to be followed so that dose to be evaluated. But on the other hand, pocket dosimeter is the active dosimeter. It will give you the active reading of your whatever being received by the radiation worker. Then these are the different type of exposure situation. Certain are planned exposure, then certain emergency exposure, and certain are the existing exposure situation, just like background in certain reasons. Then the category of the exposure, it is occupational exposure, then public exposure, and medical exposure. The next is the interaction of cell with interaction of radiation with cell. It is the direct interaction. Actually, DNA is considered as the most, you can say, target, most sensitive target while we are dealing with the interaction of radiation with matter. There are certain direct damage in which the ionizing radiation directly interact with the DNA, and there are certain interactions in which these radiations, they interact with the surrounding materials, and they will generate free radicals, and these free radicals further interact with the DNA and lead to the DNA damage. Then the dosimetry in radiotherapy. So dosimetry is nothing but it is the measurement of the dose with the help of suitable dosimeters, which has an active volume, and that can give you a reading of the absorbed dose deposited in the sensitive volume by the ionizing radiation. So we have, as I explained you earlier, we have passive dosimeter, we have active dosimeter. This is the flow chart of radiotherapy procedure. In this case, the patient will come after doing all the investigations. Then the radiation oncologist who is working in the radiotherapy department, he will ask for the chemotherapy depending upon the disease, or the radiotherapy or the surgery, because all these three modality will be very good for in certain case the combination of these any two of the surgery, chemotherapy or radiotherapy will be needed, or in some cases only a single modality is used. So after it is confirmed that radiation should be delivered to this patient, it is beneficial to that patient, then we make use of either external beam radiotherapy or brachytherapy. So there is a treatment planning. So treatment planning, so we have taken the CT of the patient with the proper fiducials to get the origin of the
Excuse me, sir.
Yes, please.
Sir, there is one humble request. Kindly आप बस 2 मिनट के लिए अपनी प्रेजेंटेशन शेयरिंग बंद कर दीजिए. हमें ना एक टाइटल शेयर करना है जस्ट
Okay.
सेमिनार का,
Okay.
क्योंकि आपको ना पूरी यूनिवर्सिटी की ऑडियंस देख रही है हमारे सेमिनार हॉल से, तो हमें जस्ट वो प्रेजेंटेशन देनी है 1 मिनट के लिए.
Okay. Kindly let me know once when I have to start.
बस सर 1 मिनट के लिए आप अपनी शेयरिंग स्क्रीन शेयरिंग बंद कर दीजिए बस, उसके बाद रिज्यूम कर लेना. थैंक यू सो मच सर.
Thank you. Hello. Okay. Okay. मैंने कर दिया. हम्म. यार मैं क्या था मेरे खत्म नहीं होना चाहता, मैं तो उस टाइम पे बोला था नहीं हो पाएगा. चल ठीक, मैं ट्राई करूँ.
Hello, Dr. Ranjit sir. Please start the presentation. Dr. Ranjit sir.
Shall I start?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Please start, sir.
Okay.
Thank you, sir. Thank you. Please share your current slide.
Okay.
Yeah. Karna.
So this is the radiotherapy process flow chart. So we have done up to brachytherapy. It is actually it has been decided that whether we go for the external beam therapy or the brachytherapy, there is a treatment planning system. So treatment planning system, before the treatment planning system, we have to do the simulation also, that dose simulation. For that, if you see this, this is a patient which has a brain tumor, and we have a certain localizers to get the origin of the certain marks over there. If you see, there is a mark, a cross, and a plus sign mark over the head of that patient. So similarly, we have on the lateral side also. So we have defined the origin from that, and from that origin, we came to know that our target volume, the center of the target volume, is at such much distance in the longitudinal direction, lateral direction, or up-down direction. Okay. So from that, we will make use of treatment planning system, and this is actually the dose distribution which we have get from our commercially available algorithms which are being used in treatment planning system. This is the transverse view, and this is the sagittal view. So after we have did the dose simulation with the help of treatment planning system, now we have to deliver this planned dose to the patient. But before that, we have to do the patient-specific QA. For this, we make use of this rendophantom. This is nothing but this is just a replica of a human body, okay, that is being used, and we will perform all the dosimetry over here. And once we are satisfied that our dose variation is not greater than plus minus 3%, then we will go ahead with the treatment.
Excuse me, sir. Sir,
Yes.
sir, how will you calculate the accuracy of the mark position in patient?
Accuracy of the mark position of the, suppose in certain cases, if it is not possible that we are exactly reproduce the position of the patient during the treatment, then we make use of different devices. We have the EPID that is used as an on-board imaging. The on-board imaging means at the time of treatment, we have the KV source and KV imager, and then we have also that MV imager and you can say the MV source. So with that, if any variation is there, we can correct at the time when the patient is there on the couch. Okay. So that comes in volumetric arc therapy or image guided arc therapy, or even intensity modulated radiotherapy. So with this, if there is any variation, we correct for the patient also. Okay. So but in case of rendophantom, if you're using rendophantom for the patient quality assurance, or the before we are going to actually execute on the patient, we can import all the contouring of the contouring, that is the normal structures, and the tumor volume to this randophantom, the CT image of the randophantom, and we can perform the dosimetry on this randophantom. And when we are satisfied that there is not greater than plus minus 3% failure, then we go ahead with the treatment in the patient.
Okay, thank you.
This is the actually linear accelerator, that is the medical linear accelerator that can generate you can say the photon energy, multiple photon energy, 6 MV photon and 15 MV photon, and multiple electron beams, 6 MeV, 9 MeV, 12 MeV, 15, 18 and 21 MeV. So this, if you see, there is an accessory. This is for actually used for electron therapy. This is the electron applicator. Okay, as you know that this is electron is a minute particle, so it can scatter too much. So in order to avoid that scattering, this grid has been applied, or you can say the negative potential has been applied, so that it will be not scatter too much before it is entering the patient body. Okay, so in electron therapy, mostly we are treating the superficial tumors, skin tumors, okay, whose depth is less than 3 to 4 centimeter. So we make use of electron therapy. Then, but before handing over the machine, daily we have to perform the output of the machine. So there are different steps that being involved. We make use of cylindrical chambers. We can perform all this on a water phantom, which is of the size of 30 cross 30, and 30 is the height, and we can perform it with the 10 cross 10 field size. That is the useful thing that we can define with the help of the collimeters we have. Okay, so then we make use of cylindrical and parallel plate chambers. These output consistency is from the TRS report 398 that we have to follow in our institute. Then with the help of electrometer, we came to know the reading. Since most of our chambers, they are air vented, so we have to apply correction for temperature and pressure, because the quantity of the air that will depends upon the temperature and pressure inside the chamber. Okay, so that we have to then we have to apply the correction for polarity of the chamber. Sometimes certain users, they will use negative potential polarity, other will use positive polarity. So we have to apply the polarity correction also. Then the recombination losses. For this, we make use of two different voltage. So this is the actually output we are finding. So every day before the patient treatment, we have to perform this so that we make sure that our we are accurate in plus minus 3%, or you can say we have a accurate in delivering of dose, and if there is any variation, that is between plus minus 3%. Then, in spite of this, we can perform the in vivo dosimetry also. That is the dosimetry which we can perform when the patient is on the treatment couch, when the treatment is going on. So for this is also useful for accuracy and precision of the measured dose and the planned dose. So in certain areas, we have found that our algorithm, commercially available algorithm, which is either pencil beam convolution or AAA, that is an analytical and isotropic algorithm, they are failed. So in that case, we make use of certain in vivo dosimeters, so that we can assess the accuracy of dose, measured dose, and the planned dose that we have done with the help of treatment planning system. So we can also measure the dose to the organ at risk. Then this quality assurance is a radiotherapy process, and the overall verification that will should be done throughout the treatment preparation and delivery. There is the estimation of uncertainty in radiation treatment at a given time, given institute, that is also verified. And suppose in certain cases, it is possible hello, okay. एक मिनट. Is it audible to everybody?
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Please continue, sir.
Okay. So it is possible that the patient will receive either low doses, lower than the prescribed dose, and greater dose as compared to the prescribed dose. So that in vivo dosimetry that we are doing, that will be early stage of estimation of such type of discrepancy. So that correction can be applied if we do the in vivo dosimetry. So next is the for different patients we have it is possible that we can measure the exit dose, entrance dose depending upon the treatment site. So these are the different dosimeters that we are using. For example, thermoluminescence dosimeter, semiconductor diode, metal oxide semiconductors, field effect transistor, MOSFETs, OSLDs, optical stimulated luminescence dosimeter, films. This is low speed films are being used. I have wrongly written over here because since we are giving a very high dose in case of radiotherapy, okay, although we are giving a very less dose in case of diagnostic. So in diagnostic, we require low speed films, but in case we high speed films, where with a small quantity of exposure, there is a large change in the gray value. But in case of radiotherapy, where large dose has been delivered, in that case, we require low speed films. Okay, so that
Sir, excuse me, sir. Sir, what is the major difference between TLD and OSLD? And
okay, so in case of thermoluminescence dosimeter, since there are certain impurities that being added, so as a result of which there are certain traps will be the electron will be trapped in the trapping centers, and that in order to eject that electrons in the trapping centers, we are either giving a thermal heat or we are giving either a light. So if you are using a thermal heat, then that will be the OSLD. And if you are making use of optical light to excite the trapped electron, then that is the optical stimulated luminescence dosimeter. So next is the 2D array that will give you the 2D dose distribution. That is the electronic portal imaging device. So in our department, we are making use of TLD dosimetry, film dosimetry, and also the EPID dosimetry we are doing. So I'm going to explain this. It hardly take me 5 minutes. So in TLDs, we have different types of TLDs. Lithium fluoride activated magnesium and titanium, whose trade name is TLD100. Then we have a lithium fluoride activated with magnesium, copper, and phosphor, which is trade name under GR200. Then similarly, we have this calcium sulfate dysprosium. Okay, that is also used for in vivo dosimetry as well as the personal dosimeter. So the TLD batches that we are using in most of the institutes, they are made up of calcium sulfate dysprosium.
Sir, as per my knowledge, all these TLD materials are available in PJ or BRC? You have purchased from BRC?
We have in our department, we have only TLD100 and calcium sulfate dysprosium. Okay. But in BRC, they have all these TL materials.
Okay, sir. Okay.
So these TLD materials, they can also use for the personal dosimetry, for the medical dosimetry, and that also used for the environmental dosimetric studies. Okay, so in certain cases, if you find that your machine is giving underdose or overdose, then with the help of this TL dosimetry, you came to know, and you can inform the engineer that we are getting this much of dose, which is beyond the limit. So he or she came, and he will do the rectification so that we will get the accurate dose to the patient. This is the TLD system. This TLDs, if you see on the left side, you will find that there are certain TLDs, rod-like TLDs, small, that is of the length of 1 mm dia plus 6 mm length. So that is cylindrical in shape with a dia of 1 mm and length 6 mm. This is the TLD. On the right hand side, we have the TLD annealing and reading system. The next is the electronic portal imaging devices. So this we have the image. It shows the this is the linear accelerator, low energy linear accelerator, which gives you only 6 MV photon beam and no electron beam. If you see on the lower side, there is some retracted arm. This is nothing but this is the EPID. That is consists of array of the detector with an active volume of 40 centimeter cross 30 centimeter. So it is either having detectors of liquid ion chambers or amorphous silicon. This is used for patient dosimetry, patient positioning, for quality assurance of various parts of the linear accelerator. Then we make use of films also. So earlier we are using radiographic films. So this film will give you a permanent record. But the limitation, one of the limitation of film is that its response will be depend on the processing conditions. And it is also affected by the temperature and humidity. So external physical quantity also have a great impact on this, you can say the information that you got from the radiographic film. So that consists of a transparent base coated with an emulsion containing silver bromide crystals. So in radiotherapy, we are making use of a slow speed film. As I told you earlier, this slow speed film is nothing but it will give you, for a large quantity of exposure, it will give you a small change in the gray value. Since we are dealing with a high dose, which is of the order of 10 raised to power 3 times more than that we are giving in diagnostic, take it from the X-rays, from the KV X-rays. So we use slow speed film. So darkening of the film, that will be proportional to the absorbed dose. And we are making use of a densitometer to measure film darkness. So before that, if you are using this TLDs, you have to irradiate your TLDs or film with the known doses, and you have to know the readings, and you have to plot a calibration curve. So next time, whenever you are applying this TLD to the dosimetry to the patient, so you have an unknown dose. From the calibration curve, you came to know that this is the number of counts, and corresponding to this, the patient will receive this much of dose. So before that, we have to do the calibration also. If you see this screen, this is a known case of CA breast. On the left side, the patient has done right breast mastectomy, in which breast has been removed, and it is treated with the cobalt-60 beam. So this, if you see these micropores, and this beyond actually on the there is certain pouch we have make use of the TLD. We have encompassed the TLD in a small pouch of plastic, and with the help of micropore, we have placed over the treatment site. So this on the right side, or the figure B, that is for the patient with the left breast mastectomy. The next is this is the latest one we are using in our department. This is the radiochromic film. Radiochromic film has a advantage that it is a self-developing. You don't require developing of the film. Okay. So and there are different EBT, EB2, EBT2, EBT3. These are the commonly used. And in this case, the monomer unit of diacetylene will undergo 1,4 addition polymerization reaction, and there will be change in the gray value. And that gray value will be the change in the gray value that will depend upon the quantity of the radiation or dose delivered. So this polymerization reaction that will involve 3 steps. This is the first step is the chain initiation, second is the chain propagation, and third one is the chain termination. So this next slide that will give you the steps that will be involved during chain initiation, chain propagation, and third one is the chain termination. Okay. Next is the summary. Radiation are used both in diagnostic and therapy. The principle of radiation protection should be strictly followed before making use of radiation. Interaction of radiation with medium depends upon nature of the ionizing radiation and nature of the medium. Radiation industry is considered as one of the safest industry as the annual fatality rate is low. Quality assurance should be done routinely. Plant dose should be verified with different dosimeters. For example, TLD, films, EPID, diodes to evaluate accuracy of the treatment. Quality assurance and dosimetry is an important component of a radiation safety system of radiotherapy department. Thank you. Any question, any comments?
Thank you, sir, for the wonderful talk. You have very well defined about the basic principles of radiations, brachytherapy, and other clinical trials. Before proceeding, sir, I have some questions. Sir, can you move to the slide 45? Yes, next. Yes, sir. Sir, how do you know that the cobalt source is the most best for in this case? Because you have other iridium source as well. So how do you know that the cobalt beam is more appropriate than other source?
Okay. So actually, this if you see the iridium actually that is a small source we are using for brachytherapy. That is only for a small fields, for small area volume. Okay. As we going to treat large volume, the dose inhomogeneity is more in case of iridium. Here we are making use of a telecobalt source. Telecobalt source which can define a field of the order of 40 cross 40, 35 cross 35 centimeter scale. Okay. So it is not possible with the iridium, which is minute in size, to irradiate such a huge volume. Okay. And in case of in this patient case, if you see, the patient's breast has been removed surgically. Okay. So only the chances that during that surgery certain tumor cell will be left. So in order to kill that tumor cell, we make use of tangential fields with slicing the tumor and also sparing the lungs and heart in case of right breast, left breast. Okay, with the help of cobalt 60 or 6 MeV X-rays.
सर मान लीजिए मुझे कैंसर है. आई एम सफरिंग फ्रॉम कैंसर. लेट अस सपोज सर आपको कैसे पता लगेगा कि आपको कैसे मतलब हमें कैसे पता लगेगा कि कौन सी टेक्निक बेस्ट है, जैसे कीमोथेरेपी इज बेस्ट और डायरेक्ट वी हैव यूज्ड द रेडिएशन थेरेपी. हाउ डू यू नो?
Okay, actually there are certain protocols that we have to follow. That is the decision of the radiation oncologist, or you can say medical oncologist and surgical oncologist. And on the basis of that, they will decide that whether we go for the chemotherapy, whether we go for the that surgery, that whether we go for the radiotherapy. So that will depend upon, because if I consider a similar case suppose the tumor size is very large and it is
Right.
not encompassing any normal structure. So in that case, what we can do, we can make use of surgery. Okay. Because
Okay, sir.
in that case, radiation has very less role. That is because as the size of the tumor increase, the inner core of the tumor that became radio resistant because of the supply, less supply of oxygen and nutrient. Okay, if oxygen is present over there, then what will happen? It will, when ionizing radiation fall on that, the electron that will be generated from the damage of the DNA, they will be taken by the oxygen. So oxygen will take that electron and DNA will remain damaged. But when there is the absence of the oxygen, what will happen? Because of the larger size, that inner core will became radio resistant. So that will be the different protocols has been, and depending upon the different grading of the tumor, from the biopsy and all the investigation for the PET scan, CT scan, MRI. So we came to know that this patient is best suited for this modality.
Sir, suppose I have one more question. Suppose we have using cobalt MEV X-ray beam. When it hits on the patient body, as we noted, it is not a monochromatic. Then it will help. It will affect the normal cell as well.
Yes. So actually, one thing that I have already explained you, that is the stochastic effect. Okay.
Yes, sir.
So because it is not possible that we can remove the tumor and give the radiation and then again fix it on the same site. It is not possible. So during the treatment, the normal structure, the tumor will get the dose, but in spite of that, the normal structure will be receive the same dose. So chances in future of the normal tissue to be get cancerous will be there.
Okay. Thank you so much for the wonderful talk. Hopefully, I will invite you next again in our seminar.
Thank you very much.
Thank you
everyone.
so much, sir.
Thank you everyone.
Thank you, sir. Thank you so much.
Thank you, sir.
Sir.
Thank you, sir. It was a very fruitful session. So now we move to our second session, which is by Ms. Jyoti, who is the HOD of Radiology and Imaging Technology, Sushant University, Gurugram. I would like to invite Mr. Rajdeep Singh to please introduce and invite the resource person. Over to Mr. Rajdeep Singh.
Thank you so much, ma'am, for giving this opportunity. And good afternoon to all. I would like to introduce our very eminent speaker, that is Ms. Jyoti. She is currently head of the department Radio Imaging Technology in Sushant University, Gurgaon. She has several publications in national and international journals. She has worked for the clinical purposes in very renowned hospitals in Columbia Asia Hospitals. Currently, she is also worked in Sharda University, GDO Goenka University as a clinical in charge and academic coordinator for several universities. I would like to request Ms. Jyoti kindly proceed for your topic. Ms. Jyoti, please.
Am I audible?
Yeah, ma'am, you are audible.
Yes, ma'am.
Thank you so much, Mr. Rajdeep sir, for this kind gesture and to invited me for this great seminar. Also, it would be great pleasure to meet Ranjit Singh sir virtually and everyone who is available over here. So I'll just share my screen if it is visible. Just let me know. Is the screen is visible?
Yes, ma'am.
Yes,
Your
ma'am.
screen is visible.
All right. So, as today we are discussing about the radiation possibilities and radiation safety measures and everything about radiation and its awareness. So, definitely, my concept on this, I'm going to present you. Today, we are in the era where we are using radiation on a very vigorous mode. That is not actually harmful, but we are actually using it in a very subtle mode that it will not give you that harmful effect it actually gives in the earlier stages. So what all are the outlines for the today's talk will start with little history, radiation and radioactivity, then what all are the radiation doses, biological effects, ALARA, and what all are the radiation safety measures we take, general safety and awareness about radiation. So, when the word radiation has been said, that actually comes in our mind that there will be certain hazards associated with it. There are so many kind of, means deadly aspects which has been outlined with it. So, this is actually not the story. We have a very formal way of radiation. So I'll start with a little history. We should know what is radiation and where from it come. So if we'll start with the very beginning, I'll just give you a brief because radiation protection, radiation hazard in itself is a very big and huge topic, and I'll just sum up and give a brief layman's introduction about it. So in the history, we actually celebrate World Radiology Day on 8th November every year because it's the day when actually radiation X-rays were discovered by Sir Wilhelm Conrad Röntgen on 8th November 1895. The name X-rays was given because certainly it was discovered accidentally. How accidentally? Because Sir Wilhelm Conrad Röntgen was actually working on some other experimental uh, process of his own in his workshop at the backyard of his house. So pretendly he was actually working on something else, but uncertainly he founded a very renowned discovery, which is X-rays. So as per its name, X-rays were put in the name because, as all the students are aware, that when we are unaware of any component in geometry or any mathematical equations, we usually give the name X, right? So definitely, because we answer Wilhelm Conrad Röntgen is also unaware about the properties of X-ray, so he have given that name at certain time. But this was the name which is get popular, and still now also we are using the same name. As soon as Wilhelm Conrad Röntgen get to know that he has accidentally discovered a bombshell while he was working with his experiment, and regularly he's actually found something very drastic change with the thing that there are some invisible rays which actually encounter to his body, and not his body's shadow. When some light comes to you, you can see your shadow at the back, but with X-rays you can't see only the shadow of your whole body but only with the bones. Why it is so? Because it is somehow penetrated to the soft tissues, means the human body, and only get absorbed by the high atomic number objects like bones. So Sir has actually seen his bony structure and other metallic structures on the screen, on the phosphorus screen, which has been present in his lab. So definitely, at that time, he actually given at that era of 80s, late 80s, actually it was a big boom to the medical industry because uh, when it is so difficult to treat any patient, because every time, even for a simple fracture or even not a fracture, they used to have a proper surgical instrumentation to go on through with the patient to check out whether what scale of fracture is being there. All right, so with X-rays it has become so easy to actually look into the body parts of the human body without even a single incision. So that was actually a big boost to the medical profession at that era. Now, this news has been stolen by every news, what all media which has been available at that time, magazines, newspapers, everything has been, covered with the news that something like X-rays has been discovered and everywhere. Now, that day, if you can see a third image over here, which is of an ad from 1896. So I want to show you this ad because the purpose of today's talk is about radiation protection. So over here we can see how vigorously radiation was misused at that time, because we are not aware that radiation actually have some side effects. So over here, if you can read, if my, I don't know whether it is visible or not. So over here it has been written that, oh, my head is oh, my poor head, it is hurting, please give me a dose. It, you can see by 25 cent you are getting 8 dose. Wow, we are paying so such money and getting a high dose of radiation to get rid of headache. I don't know, from my whole career, I don't think that radiation is for meant for headaches. Right, definitely. And everyone knows that this is not the scenario of X-rays. It actually meant for something else. But at that time, people are using it like anything. In fact, Sir Wilhelm Conrad Röntgen, he himself, in for many conferences, for many news reportings, he have given his videos in which he was actually drinking the cup of tea, and he's sitting on a chair and in front of an X-ray tube where all the images has been being placed on a backside fluorescent screen, and that's video has been recorded and played in certain music album videos where people are actually fluing the musical instrumentation, and x-rays was taken out to make it more, you know, drastic, to be more attractive for the audience to be seen. So this is what practices are being followed up, which is actually definitely not so ethical, but that time they are not aware of it. That's why they made that mistakes. Now, if we'll talk about a little history about India, so we in India, X-rays has come to us in early 90s, and in cargo, in definitely in the army, in Bernard Institute of Radiology and Oncology, which was earlier was a government college in Chennai. So at that time, we used to know about X-rays in a very certain stages, and later on, it has taken a good grab into the market of radiology, has been spreaded into the medical industry, as hence shown a prominent growth in the field of medical and healthcare field. So before understanding the radiation hazards, first we should know what is radiation is. So basically, radiation is an energy. It's a form of particle or a electromagnetic wave. So over here, if you can see an image which shows two types of radiation, which is non-ionizing and ionizing. So definitely the non-ionizing radiation is not that harmful. The ionizing radiation part is actually the one which actually causes the radiation hazard effects. So ionizing radiation is something that it is a type of radiation which actually have a sufficient energy to remove one electron from its atom, and that is where it actually plays its role in the hazard portion. So in this image, you can easily see, in the image which has been available over here, you can see there is non-ionizing radiation and there is an ionizing radiation. So in non-ionizing radiation, you can see radio waves, microwaves, infrared, visible light, ultraviolet, and ionizing radiation. We have alpha, beta, gamma, and X-rays. So you can see we are surrounded with radiation. We have radiation each and every corner of this. Means wherever you are sitting, you might be sitting in your office, your hospital, or might be at your workplace, at your home, wherever you are sitting, you are surrounded with radiation. Yes, that is the truth. That too, not only non-ionizing radiation, we are surrounded with ionizing radiation as well. That we'll consider later what all are the sources of radiation. We'll see in the upcoming slices. So we have discussed about ionizing radiation and non-ionizing radiation, but there is another factor which is radioactivity. So I'll come on that. Before that, I'll let you know the difference, that radiation is the dose which we receive from whatever source of radiation emitting is there. But radioactivity is the part which actually emits the radiation from certain natural source of radioactive materials, and with certain man-made source of radiation as well. So Dr. Ranjit sir has explained it very nicely, that what all are the radioactive components and treatment prospects and everything. I'll tell you about the introduction of radioactivity and what are the radiation prospects which has been there, and what are the radiation protection which is covered the agenda of the radioactivity. So radioactivity, it is actually, if I'll just give you a brief history of radioactivity, then you must have heard about Curie family. So we'll give this credit to Madame Curie and Marie Curie, as they have invented the actually discovered the radioactivity. That was also a natural discovery, and they also have discovered it in 1898. And they actually given a great initiative to the medical field, that it actually exists. And now what all are the uses of radioactivity they have posed? So definitely that time it was not being that aware that it actually cures cancers and other radiation therapy treatments can be given. But yeah, this has been used for many other experiments, in scientific way, in the defense way, and so on. So if I'll talk about, I'll give you a just little in you know knowledge about Marie Curie. So if we'll talk about Madame Curie, she actually died with aplastic anemia. Why so? Because she is the woman who actually holds many Nobel prizes in her account, which among that she also is the first woman who actually received Nobel Prize, that too in two different categories. So that is also she is known for. But due to her own discovery, she is the woman who died. And not unlike other scientists whose workplaces are being kept for as in museums and visiting places for the all the visitors and to the tourists, her workplace has been kept confidentially locked and prohibited to visit. Not even her workplace, even her graveyard is being kept for prohibited to visit. And why so? Because she has taken the radiation dose at that extent that she died with the aplastic anemia. Also, her graveyard is still emitting radioactivity. As sir has said that human body, Ranjit sir has clearly said that human body also have certain amount of radioactivity in themselves, radioactive material that they have, and that can be even available in the ashes of a burned body or in the molted portion of the dead body. So her dead body still emits radioactivity. That's why her graveyard is also a place which has been prohibited to be visited. There is no superficial thing or something is there. It is scientifically been prohibited because of the radioactivity she emits from her graveyard, and also from the workplace where she used to work, in her labs, in the workstation where she used to do all the experiments. So everything has been kept, because everywhere there is certain radioactivity being produced. Why so? Because she used to carry radioactive materials in test tubes, in bottles. She carries that in pocket and travels everywhere. Also at her home, at her drawer, and everywhere there are certain number of radioactive material available, because she is doing the experiment on them. And also, might be or might not be, she is aware of the radioactive and its hazardous effects. So, if we are talking about this much about radioactivity and radiation, and so far we have discussed only the negative impact of radiation and its hazards. So, do we think, or should it comes in our mind, that radiation is only going to give you devastating effects only and nothing good to be over there? Well, if this is no, definitely not. If this is what the story, then you and we are not in this profession. We all the senior faculties and all the pioneer bodies and eminent personalities of radiology will not be in the field. Neither you have taken admission in the radiation department, neither I have chosen this profession for the same. This is not the story. Definitely, radiation has definitely its own impact, like any other thing which also have its side effect. I'll give you a simple example. Everyone, I think no one is being left out over here who has taken medicines. Even to nowadays, even if a fetal child get born, in just the early days of its birth, they got the dose of radiation, sorry, not radiation, medicinal doses at the time of their joining. So at the time of their birth. So how they actually give that doses? in a certain amount, in a appropriate dose limit, in a weight, height, or age factors which is associated with the dose of medicine they have taken. So fetus, whether it is a pediatric, whether it is an adult patient, whether it is a generic patient, doesn't matter. Everyone, or whether it is a patient or not, we all, some on another day, we have taken certain medicines. And we are also aware that medicines have its side effects in certain manners. Either some patients are allergic to certain medicines, or might be the dose which has been given to the patients are sometimes high as per the limit which they have to be given. So in that way, if we are aware of that medicines are having side effects, still we are taking it. Why? Because we know that the doctor who is prescribing the medicines, we are trusting him that they will give us the best of it. More on, we are aware that the dose we are taking, if we'll take it into the limit what doctor has prescribed, then there is no side effect and nothing will be going to get us. And we all know that if we take a particular dose of a particular medicine in the morning, we should not repeat that dose in frequent way. We should only take it after 8 to 10 hour of 6 to 8 hour gap in between the first and the second dose of that single particular medicine. Whether we are getting fever or whatever, we take that medicine in a certain gap only. We don't take it repeatedly, because we are aware that if we'll take it repeatedly, we will get the side effects. And if we will not take it repeatedly and will take in a certain manner, we will definitely going to get the best of it efficiency. The same pattern and the same way is followed in the radiation doses as well. Radiation is also given on the basis of dose to the certain levels of patient, whether it is pediatric, healthier patient, thinner patient, whether it is generic patient. So whosoever is in front of the X-ray source or the radiation source get the radiation dose in an ampute amount. One more thing I will love to say, that in medical profession we work on a motive, that is risk versus benefit. So if the risk is on the lower side and the benefit is on the higher side, then only we take the risk. It is applicable with the with medicines also. It applicable on the operational procedures as well, and it is applicable on the radiological procedures as well. Okay, so when we are taking risk, that means there is definitely is going to be a good benefit out of it. If the risk is higher and the benefit is certainly less, we are not going to perform that. And for medical profession, the life of the patient is the highest benefit, nothing else. Moving on to the topic. So we are talking about the radioactivity. Radioactivity, we will say that if Marie Curie's graveyard is still emitting the radiation, then radiation is not going to be, radioactivity is not going to be vanish, and then how may we use it? Right. So if this question comes in your mind, then the answer is radioactivity, like every other thing, has a life. Okay, they have a life which actually going to end at certain time. Yeah, the time depends, that the time is higher or lower. Might be the radioactivity we are using at certain time have a half-life of 5 minutes, or might be a radioactivity we are using at certain time might be have a half-life of 30 years. So there is a difference, right? Okay, what is half-life? If it is not that rocket science, you might have heard about it or have studied about it in the class 9th, 10th or 11th physics. It generally, when, if I'll take an example, if I have a 2 grams of radioactive material with me, okay, 2 grams, okay, so, and its half-life is 5 minutes. So after 5 minutes, the radioactive material from 2 grams, it will automatically going to reduce to 1 gram. And if you think in another 5 minutes it's going to get vanished, no, where there is the half-life comes in. After 5 minutes, it's going to become its half of its original weight. Means from 1 gram, it will become 0.5 grams. After that, if you will, after more 5 minutes, it will become 0.025 grams and so on. So it will be going to continue until it gets zero. So just a 2 gram part with half-life of 5 minutes also takes hours to get reduced to zero. This is what the scenario is. That's why if a radioactive material is of half-life of 30 days, okay, or 30 years, so it will going to definitely going years and years to get reduced, and decades even to get reduced to its zero. Or might be some of a kind of radioactive material has been taken by Madame Curie as well. That's why her graveyard is still emitting radioactive material. All right. So this is what the half-life chart which will can shown here, and this is the definition of half-life, which is technically physics of it. So I'm not going into the physics part and the technical part. Moving on, there are some units for radiation. So we have exposure, which has been denoted as R, and it is the amount of radiation per unit mass of air. Okay, and so these are some units which we use to measure radiation which has been absorbed or been produced. So absorbed dose is the amount of radiation which has been absorbed by a unit mass of body of a patient or a body whosoever received the radiation. Equivalent dose is the composition of all those doses in a one way manner, that what all are the radiations which has been taken by the body and what is the impact of it. Okay, so this is now will come to, we have discussed earlier about ionizing radiation and non-ionizing radiation. So the non-ionizing radiation part is not that much affecting us on a very good extent. It is only like visible light is also part of non-ionizing radiation, alpha, beta, radio waves, microwaves, which is our day-to-day life thing, which is also part of non-ionizing radiation, and we are surrounded with it. But that is not actually irritating you that much. The ionizing radiation is the thing which is actually irritating you at a very good extent. In that, it comes like X-rays, alpha, beta, gamma. So we have discussed something about X-rays. Now we'll discuss about alpha, beta, and gamma. So I'll show you. Alpha is one of the type of radioactive or radiation which actually emits by certain radioactive material, natural and man-made both. So it actually have a massive way of ionizing anything, means to remove atom electron from its atom. So it have a highest tendency to do that, but it also have a negative part, which is a positive thing for us, that it actually have a very low, means very minimal penetration power. It means if alpha emitting sources is in present of you.
Sorry to interrupt, Jyoti ma'am. Sorry to interrupt you. Right now your slide is moving on. Right now this is okay. Your slides are stuck.
Okay, now it is moving.
Yeah. Thank you.
Okay. So the alpha particle is actually have a negative impact, that it has a low penetration power. So we use it when we need superficial treatments, like if there is any oral cavity cancer, or there is any rectal cancer, means where we can directly introduce in a retrograde way the radioactive material to the body, where we can get the superficial radiation damage. In these kinds of things, alpha particle has been used. Now we have beta. Beta is the one which actually have intermediate penetration power and intermediate intensity of radiation. So it can be absorbed by not the piece of paper, but by a sheet of plastic. A thin sheet of plastic can also absorb beta particle. So if there is a source of beta particle, if we are hiding besides a plastic door, that will also going to help you a lot in getting safety from radiation. Now we'll talk about gamma. So gamma radiation, gamma rays are those who are somewhat similar to X-rays. The biggest difference I find between both of them, means they are similar in case of speed, they are similar in case of frequency, in case of the intensity of producing the penetration and everything. But the biggest difference between both of them is that X-rays are being in control, means we can control the X-rays by manual description, because it actually produced by the man-made source. X-ray machine is a man-made source. It's not been available in the nature. Where the gamma products are available, gamma radioactive materials are available in the nature, so we can't control its emission. Once it start emitting, it will emit up till the end of its half-life. Okay, but X-rays, it starts with the human pinch. If you will switch on the button, like lights on, X-rays on, You will switch off the light, switch off the button, lights off, X-rays off. It is like that. So you can use the X-rays for the fraction of seconds and for a longer duration up to you. So over here in this image, you can clearly see that alpha particles can be stopped by piece of paper, where beta particles can be stopped by a thin plastic sheet, and gamma particle, where first X-rays also penetrates from paper, plastic, but get absorbed by lead and equivalent material. Whereas X-rays, whereas gamma rays, at some extent, they got absorbed by lead material or equivalent, but after that, X-rays, gamma rays, because it produces in a massive amount and that too on a continuous mode, so it also get emits by the lead barriers. So for gamma rays, it's very highly, we use it in a very highly protective mode and at a very serious modes where it is efficiency is on risk versus benefit mode. Okay, so to understand this concept, I'll show you one video. Let me know if it is visible to you. So three humans are being resembled as alpha, beta, and gamma. So you can see in, hope you have seen the video. Is the video is visible to all of you?
No, ma'am, it's far not playing.
Okay. Okay, basically the video says that there are three people who are running. One is alpha, beta, and gamma in an animated way. So the first one actually stopped in front of paper. The another one gone beyond the paper and stopped in front of the plastic sheet. The third actually penetrates the plastic sheet as well, but goes to the concrete or the lead wall and stops there. So that means the third one was gamma. So over here in this image also you can see that the beta emitters get uh, somewhat absorbed in plastic, but goes only till 1 centimeter or 2 centimeter, not beyond that, and can be absorbed by it. By lead, they can get a good absorption at lead by lead. For gamma, it actually get absorbed by, means it actually get penetrated by beta, lead barriers also, whenever it is, when it emits in a very high intensity and a very massive way. So how we will get to know whether it is a radiation zone or not, and how we will protect for both. For those who are working in radiation zone, first we'll talk about that, and for the general public also we'll go in the next phase. So for those who are working in radiation field, definitely should be aware that how they should work on the way. So there is certain because these rays are definitely not visible from the human eyes by the naked eyes. So how we will predict that there is radiation or not? So we have certain meters or dosimeters for both, for the area monitoring and for personal monitoring. So for area monitoring, wherever we are working with radioactive materials, we should be very much uh, used to of area monitoring devices, which actually gives you a brief introduction, brief details about the radiation and a minute details of radiation as well, that there is a radiation, because we are someone who is technically authorized to use the radiation and to play with it and to actually use it, because we are educated and skilled and have a degree who can use it. But those who are actually not from the field, and those innocent people who are not even aware about the radiation doses and everything and the hazard associated with it, we are the one who is actually responsible to take their care for the same. So this is the radiation monitoring thing, which is for area monitoring, and you should should be available in all the radioactive areas, and this is the one of them. We have even more area monitoring, like Giller-Muller counter, GM counter, we call it in a general, and we have survey meters and so many other monitoring devices which is available as per the requirement and the workflow of the organization. We have certain personal monitoring devices as well. Here you can see there is TLD, which has been provided to the radiation worker, film badge or OSL, and we have also a pocket dosimeter, which has been available to keep like the pen-like structure, which we can keep in the pocket and can measure instant radiation on the source. So these all are the why, and now why this kind of devices are available, and if it is available, where it is. So basically these devices are available to the radiation professionals only, those who are certified radiation professionals. Their data has been received from the national radiation department, which for India it is AERB, which is a part of BARC, Bhabha Atomic Research Center, which is a part AERB. Okay, so among BARC's 17 division, AERB is one of them, and it is actually responsible for all this. Now, which we are following, it is Indian. It is like national policy which we are following, national guidelines which we are following. But about international, so we have ICRP also. They provide international guidelines. Like WHO provides guidelines for the worldwide, but those who countries who actually want to follow it, they actually resembles that. Similarly, for ICRP, those countries who wants to follow them, they actually resembles them and take the guidelines every year. So India also follows that, and we also have our individual, association, which is also following the guidelines and provided it to each and every corner of the country. Not only in India, but even many countries of Asia also following ARB and ICRP. So in that way, we are making decisions that whether, because not every country is similar, right? Some lives on a higher altitude, some lives on a lower altitude, more on their the mining part and the internal structures of the earth crust have different types of mines and radioactive material available over there. So it is definitely different for certain regions of the earth where radiation zone is somewhat higher and somewhat lower, so radiation dose is different for everyone. I'll give you an example. Like everyone who all are sitting on this platform available on the screen, or whether whosoever is sitting anywhere, we are surrounded with radiation, that too non-ionizing radiation, or not only non-ionizing radiation, we are surrounded with ionizing radiation as well. How? Because the building material we are using, that is also emits radiation. The ground which we works on, or the agricultural ground we grows the food on, actually emits radiation. From not only from the earth we get radiation, a high dose of radiation from the cosmic rays and the outer terrestrial radiation also available. So we are surrounded from the all 10 corners of the zones, we are getting radiation from each and everywhere. So how will, if this much radiation is available, why we are surviving and how we are surviving? So for that, the answer is completely easy, that for certain dose limits our body is being prepared. But if we'll get radiation dose more than that, that is going to affect the thing. So definitely radiation have a certain threshold for it, have a certain limits for it. Beyond that, there is definitely radiation damages, but before that or in limits, there is no or less radiation damage. All right. We are coming towards the amount of radiation we receive. So basically, I'll denote this into two parts. There is natural radiation and man-made source of radiation. So I'll give you a very surprising note on this. Those who are from medical profession might know it, but those who are not from medical profession or from radiology profession, for them, we are getting if a human being lives, for example, if we take under consideration a person lives for 100 years. In that 100 years, from the day he taken birth and the day he died, in that duration, the duration of lifespan can be 1 day of a person. 11 years, 10 years, 50 years, 70 years, or 100 years. Whatever the lifespan he follows, the radiation he received in the entire lifespan, the 100% of radiation he received in entire lifespan, only 18% is man-made source of radiation. Rest 82% radiation, 80 to 82% radiation is from the natural source of radiation. Means the person is getting most of the radiation he has absorbed in his body is from the cosmic rays, the radon gas which is available into the earth crust, in the building material radiation, and every, because the building material somewhat also come from the earth crust only. So this is how it actually regulates. The body actually receive 80 to 82% of radiation from the natural source of radiation, but not by the man-made source of radiation. Now, where the man-made source of radiation come from? So it is like your diagnostic x-rays, we have radiotherapy, nuclear medicine, or all those diagnostic radiation part, and somewhat we have nuclear reaction, nuclear power plants, atomic explosives, these kinds of things. Actually, the human receive the rest of 18% of radiation in his complete lifespan. So here is a graph which actually shows the radiation intensity. So you can see the radon having 55% of radiation, means the highest radiation of a human body is from radon gas, which is available in the earth crust and some of the building materials as well. So what should be a human do to preserve their body from radiation? So for occupational radiation, means those who are radiation workers, they should get a minimal radiation dose for an year of 5,000 milliram, and for the whole body it is 5,000 milliram, for lengths of 15,000 milliram. Don't get confused by my chart and Rajit sir's chart. It is far similar, only that is they have used the different unit measure that I have explained in the earlier slides, and I have measured some different units like centimeter and meter difference. Okay, so there are certain limits of radiation to be taken by occupationalists. Now I'll tell you, it is 100 times less for a non-occupationalist, means those who are public, who just come for their own radiation doses for their treatment or some or another reason. They are comes in general public, and they should not receive the radiation more than the limit they have been given. So this is for the occupational. Now for the general public, we have radiation dose 100% less than that, means 100 times less than that, not 100%, not 100 times less than this. Okay, so why radiation dose has taken into a certain limits? As I said, medicines also have a limit to be taken, or to the dose which should we take, should be a limit. Similarly, radiation also have certain limits. So why radiation has that limits? After that, what will happen? Definitely there will be radiation hazards will be going to happen. Okay, so radiation effects are somewhat in stochastic and deterministic. Stochastic radiation effects have a threshold, don't have a threshold, where the deterministic, as per its name, determined, so it actually has a threshold. And as per the dose increase, the severity increase. But in as per the stochastic way, it will, with the dose increase and the probability will increase. In somatic and genetic is a part of stochastic a type of radiation biological effect. In stochastic, there will be a damage which has been shown into the patient individually, and in genetic, it will be going to show into the offspring of the patient. Like if a person who has received radiation beyond the limit which should be given to them, if they have received it beyond the limit, then he can be served with somatic effect. If the radiation is given to one go, it might be give somatic effect, means if a high dose of radiation has given at a one single time, means somatic effects can be seen. And if radiation dose has been given in a certain amount for a long period of time, then can be genetic effects can be seen. Genetic effects can be seen into the future generation of the patient. So that is the biological effect of radiation and how it works. We'll see in the next slides. First of all, we'll show you the radiation effects which we are talking about. This is a burn effect. Like if with 500 plus rad of radiation if we have used, so you can see certain burns on the finger of the patient. In the next image, if you can see, there is 5,000 plus red has been used. So you can see the complete hand of the patient has been burned, just like an acid attack or something, or might have the patient has gone through a burner or something like that. So you can see a high grade of radiation burns on the patient's hand. In the third image, you can see the patient is the one side of the patient is completely burned. This might has been caused due to an atomic energy blast or any attack or something like that, or might be any explosive with which the patient has been encountered. Just like in Hiroshima and Nagasaki, means the place where the Hiroshima and Nagasaki the blast has happened, that actually left with nothing, but in at certain distance, at the certain diameters, many people had get lesser effects compared to the isocenter, but on those less effective areas also people have get this much burns, which you can see on the screen. Okay, like bomb survivals on those, so they have get. And what kind of damage this is you can see somatic damage which is been directly to the patient's body. Now what is like if we'll talk about the genetic damage and other kind of damage, so that will come into the DNA damage. So what will happen, radiation actually goes, as we say, it is a free radical. Radiation actually is the thing which actually have the efficiency to replace an electron from the its own atom. So that role it also plays with the DNA strains. We have a DNA strains. Yes, we all know that DNA is it goes in a parallel two strains connected with the ATPs. So and the strengths in between it. So what will happen that whenever the DNA is present in your cells, in your whole body is what your body is made up of. Your body is made up of organ system is made up of tissue system, and tissues are made up of cells, and cells are made up of certain parts of it, like, and include in that it has a nucleus, and nucleus contains DNA, RNA. So DNA, if we'll talk about, so DNA has the tendency to get exposed by radiation and get the DNA damage. But you will say, with every radiation damage, do we get the DNA damage as well? So answer is no. It's not like that. With certain high grade radiation, because the radiation which we get at the X-ray lab or any diagnostic center that is hardly harmful for you. How it is possible? Because only the radiation which get absorbed in your body will going to give you any interaction with might going to get any interaction with DNA. Otherwise, all the radiation which is going to penetrate through your body and going to create the image of your internal body structure, that is neither going to give any kind of DNA damage or any kind of radiation damage, because those radiation actually has penetrated throughout your body and went away. Your body doesn't contain that radiation into it. So that's why only the radiation which get absorbed will only going to get can be a cause of DNA damage. Now there are two ways these kinds of DNA damage can be occur. So there is one is direct and the another one is indirect. Direct way means directly the X-ray has encountered with the DNA and given the damage. If I take the example of Hiroshima and Nagasaki, people get direct DNA damage at that duration because they are so near or so close to the direct radiation source. And what result they have given, if might they have survived from that incident, also their future generation till date, their future generation are being born with some kind of birth disease or means the malfunction deformalities that from the birth, from the time of birth. Okay, so in that way radiation gives damage to, if not direct damage, then indirect damage. Now, what is indirect damage? So, in the body, we know that our body is composed of 75% of water, and water contains hydrogen atom. So, DNA actually reacts with the hydrogen atom and creates a hydrolysis. Okay, so that radiation oriented hydrogen actually cause the DNA damage, which is a very rare case and can be occur at a very certain high dose limits of radiation when a patient has taken a very high dose of it. So this is a radiation relationship of radiation dose and cancer. So you can see definitely it clearly shows that with the higher dose, the efficiency or the possibility of having a certain disease or cancer can be increased. I request the candidates to please mute yourself as it is causing a background noise. So, what are the radiation safety measures, or both for the professionals and for the layman's people, those who are not aware about radiation and everything? So, definitely we follow a simple rule, which is ALARA, as low as reasonably achievable. Okay, so in that we follow time, distance, and shielding rule, and contamination control rule. So time means we should be in the radiation zone or in the radiation exposure area for lesser to lesser time, and the distance should be increased. I request to the organizers kindly please ask the Anas Ansari to kindly mute themselves.
Hello, Mr. Anas Ansari. Please switch off your mic. Anas Ansari, please अपना mic switch off कीजिए. Madam, he is not listening. Hello.
If possible, please remove the candidate, or you can forcefully mute the candidate as well.
Okay. Okay, ma'am.
Thank you. All right. So we are talking about the time, distance, and shielding. So time should be minimal in terms of radiation intake. Distance should be as much as possible. There is inverse square law which is associated with it. I'll explain that in the next slide. And shielding. Shielding means, as we have said, that alpha, beta, gamma got absorbed by paper, plastic, and lead, and X-rays also get absorbed by lead. So we can hide ourselves in the back of these shielding materials. Okay, and then we have contamination control. For example, if a radioactive material has a spill, might it fallen down from the hand? We are all human, we can make mistakes. If any kind of spill has been meant, or any radioactive material has been kept out, so the contamination control is one of the things. Okay, that will also going to study in the further slides. So inverse square law clearly states that if it is inversely proportional to the distance of the source, means if you are standing at 2 meter away from a source, if you will get one half of the radiation dose, but if you are standing at 4 meter away from the radiation source, you will going to get 1/4 of the radiation dose, and similarly goes on, means inversely proportional to the square of the distance from radiation score. How the distance will going to increase, the source of radiation is lesserly going to impact you, or the radiation is going to get its impact by the half of the square, means one directly inversely proportional to the distance of the from the source. Then there is one more thing for general public. I'll say that there is pregnancy, and female patients are more prone to radiation in compared to the other public, pediatric, generic, every. So why female and especially the pregnant women are so prone to radiation? The female, especially it start from the female, those who are of childbearing age. they should not only for the professional, it is definitely the duty of the professional to take care of the aspect of those females who are of childbearing age should get lesser radiation or no radiation at the certain times, and if it is necessary as risk versus benefit, so we should give them radiation with with proper protocol and everything, which should be taken under consideration at the time of exposure of a female, that too of childbearing age. Why it is so? Because the female might or might not be pregnant, and if she is pregnant, it is going to very deadly, it is going to affect the at a very deadly extent to the fetus. Okay, so that is why we, before examining any female, you all are going to become radio technologists in the future ways, and going to work in reputed hospital diagnostic center, or might be entrepreneur of your own setups. So at that time, you are all degree holders of the profession, where you should be know that the all the generations of ours, of our country, should get a healthier life. This is what for hospitals and everything is meant for. So definitely it is our duty also to make it possible by spreading the adequate amount of awareness to all the pregnant and even the females, that radiation is harmful for their fetus, and if she is might be pregnant, they should clearly state that to the professionals and the doctors and whosoever is available, or nurses, whosoever is available or she is comfortable with, can pronounce that this is what she can be pregnant, or she has left or missed her LMP and can be pregnant. So in that way, we will not proceed the examination, or may postpone the examination as per it. We have certain rules for that: 10 days, 24 days, and 28 days rule. In that, it says that if in all those days of menstruation cycle of 28 days, the female should get radiation dose on all those days, which is completely safe, and the female can't be considered to be pregnant in an early stage. Like first 10 days of LMP is the best part, and rest can be done if there is any case of emergency, or any kind of risk is there. If there is non-urgent x-rays, that can be done after or in this phase. So this is what for pregnant or suspected pregnant women, non-pregnant and suspected pregnant women. If we'll talk about the pregnant women, so pregnant women are strictly prohibited for radiation doses. But as I said, if there is certain emergencies, or might be there are certain kind of risk which is higher than the benefit, then we should consider their x-rays or CTs or whatever is been required. Suppose there is a female patient who is pregnant, and uh, that should not happen, but might she has met with a trauma, she's been met with an accident, and surgery or a kind of fractures has to be seen on an urgent basis. So what we can do, we'll first try to cover the patient's womb or the abdominal area with lead aprons from both the sides, not only from the front but also from the back, to get minimal exposure of radiation, both the primary and the secondary, means the soft x-rays and the hard x-rays, both in a very minimal amount, or how much is possible. And after that, we'll do the x-rays. And if there is certain kind of injuries in the abdominal portion only, then definitely the risk versus benefit is there, and we'll if you are going to save the fetus, you will say that we are not going to give any exposure to the fetus, and mother can suffer. So let me remind you one thing: if only the till the time mother is breathing, the baby will going to breathe. So if the mother's life is saved, that then only you can save the baby's life. So that is why you have to save both's life if it is possible, otherwise save whosoever comes first. Okay, so this is what the thing. And now, what are the effects on the fetus, if we'll talk about that? So definitely it will be all or none effect can be there, means might be there is no effect of radiation on the patient. Yes, that is also can be possible. Might the radiation dose has not actually encountered with the patient, the fetus, and might there is all effect, might be the fetus can die or miscarriage or a stillborn can be considered. Malfunction is the most common example. Means if radiation dose has been kept and a patient has suffered, the fetus has suffered with radiation, they can get a malfunction, cleft lip, or any kind of deformity, or any kind of birth disease. By birth disease can be occurred. Okay, so there can be mental abnormalities and so many things. Also the patient can born with carcinoma, so these are the things can be occur. um, One more thing I want to tell you, we all have heard one or another day that pregnant women should not go in the light or in the direct sunlight when there is solar eclipse. Even I, in my earlier stages, I thought it is a myth or just a superficial thing, but actually it has a very significant scientific theory behind it. As at the time of solar eclipse, there is a high amount of radiation into the surrounding. Means the cosmic rays intensity is actually raised by 10 to 20%, right? So by one, it get actually 10 times or 20 times higher radiation dose in the cosmic rays. That's why at the time of solar eclipse it has been advised to everyone, if it is not so urgent, please try to stay at under the shade at your home, at your office, wherever you want to go. You just go beyond the time of that ellipse. So it has been prescribed, but people follow and some might not. But actually, there is not only myth. It is not only a myth. It is not only a superficial thing. It is actually scientifically true that the radiation dose is higher at that duration, and it actually affects the most to the pregnant women, because fetal are so prone to radiation. Why? Because they are at that stage, it's developing. In the whole first, second, third trimester of pregnancy, the fetus is continuously developing, right? So there might be continuously division of the cells, and the new cells are forming continuously. And at that time, if imagine the cell containing the DNA get breaks, then what will it going to come up with the result? Definitely any kind of malfunction or any kind of deformity with the patient. So this is what actually it is. So here it comes with safety reasons and aspects for the female or pregnant women. So what is the preparation and safety measures everyone should take off? So radiation source, it is first of all definitely the duty of you and me who are certified radiation workers to do the concern and take the responsibility to work into it. We are the only one who know the highest amount of, we are sitting for an hour and we are discussing about radiation. Out of 100, those who are laymen only going to get 50% or 60% of knowledge of it, because it is totally new concept for them, and they will get a very little amount of information about it. We are studying it for more than 4 years, 5 years, and working into it in this direction for so many years. We have a degree for the same. That means we are certified peoples who actually know the best and the most of it, right? So we are the only responsible. It is either written somewhere or not. It is sensible thing we should be aware of, that if you know only how to play with fire, you should not hand it over to someone else, right? So this is what the concept behind it. We should be aware that what radiation hazards can be happen, and what is the safety measures we should look into. So definitely, whenever we are working with radiation and any kind of radioactive material, we should keep it logged. Means a very good logbook should be maintained, that what is the date of this radioactive material, what is the date of that, when it has been opened, when it has been discarded, when it has been used, and when it has been buyed, or when it has to be traveled, and when it's to have be kept for log. So these all information should be kept very well. And also for the X-ray units, because as I said, X-rays are not visible from neck diet. It's just like we on the switch and we off the switch. But sometimes, because the machine has been meant for certain materials, aluminum, lead, iron, like that, alloy of them, so might be there are some cracks, might be there are some kind of leakage of radiation from those machines as well. So what you have to do on that aspect, you should maintain quality assurance and quality control of the machines at a very good extent, at a very regular extent, to know about the machine and its leakage and the possibilities of get contaminated to any of the patient, right? So this is what it is all our responsibilities. Now, If you will maintain all those things, no one is going to get extra radiation dose, neither you yourself, neither the patient. It is not only harmful for the society and the patient, it is harmful for you and yourself as well. So I don't think anyone wants to get radiation without any reason, and want to disturb their future generation without any reason as well. So keep an eye on all those machinery and their malfunctions and every kind of impact which actually leads to radiation leakage. So these handle the machine very firmly. Don't use it like means very roughly, that they can got cracks and radiation can leak through it. So you should have to take care of all this. All right. So personally, workers should be trained, qualified, as I said, disciplined and appropriate to handle those radiation-oriented equipments and radioactive materials. Right? If there is some emergency cause, they should also be prepared for that as well. Now, communication should be very clear among all the staff, that if it has happened, means if any one of you have worked in a hospital or have done training or something like that, you might know that we give a handover registered from one staff to another. Why it is so? Because the information should be continuously carried forward on a regular basis and kept logged in, as it should be. It can be a reason of any kind of contamination or hospital or radiation accidents. Okay. Now, training and exercise is another important part. The training, and it is not like that you have done a 3-year degree course or a 5-year master's course and you are well trained in the profession and you don't need any another training for the same. You are right now also sitting for a training only, right? Because we should get updated ourselves for a recent trends, for recent updation in the new techniques and everything. What all kind of, suppose you have studied it right now, after 10 years we have developed with a new isotope which have a very good impact on cancers, but it also have a very high radiation hazards associated with it. You are not aware of it. You have studied it in 2022, and after in 2032 there is a new isotope and you are not aware of it. So how may you will get to know about it? By rapid trainings and rapid updation, only you will get the upgrade. Otherwise you will stay on what you are actually, and you are actually making yourself and the patient suffering for the same. Now, if suppose it should not happen, but if suppose there is kind of a radiation emergency happens, so what should we do? In a very short and crisp way, I've explained it. We should follow SWIM. SWIMS. Now, what is that? First of all, stop. Stop the spill, not yourself. Stop the spill. If there is any kind of radiation leakage, any spill is there, any, suppose you are holding a radioactive material in a liquid form and by default you have slipped it out and there is a spill on the floor. So what you will do? Stop the spill. How will you do? There will be some kind of tissues or something like there, you can push it out. If it is the case of X-ray tube or CT, you can switch off the X-ray tube and CT from a complete electricity breakage. They are man-made source of radiation and can be controlled, so you can simply switch off the switches and make them stop for the while, until and unless the professionals come and make it repaired for the use. More on warn. Notify everyone in the department and area that please leave the room or please get out of this region and empty the certain diameter of radiation, so that the radiation should not affect anyone. Also, you as a responsible one, make yourself aware of it. First stop the spill, and after notifying everyone, isolate yourself as well. More on after isolating, inform the RSO, radiation safety officer, that visible and mannerful action should be taken place. Minimize the radiation exposure. And for minimizing the radiation exposure, this is how possible when no one is there in the radiation zone and time distance shielding rule has been followed. Now, the another part, the main important part is survey. Now, how may you do the survey? We have already discussed in the earlier slides that there are certain area monitoring and personal monitoring devices available, which has been given to the verified, skilled radiation worker. So you will also have that, and you can check for the area radiation dose. If there is any radiation still left, make the necessary things, and after that only the normal workflow will be going to continue in the region. Okay, so this is all for today. Thank you everyone for listening. Anyone, if they have any questions, can come.
Uh,
Also, I would like to say to all the organizing team that I have heard a lot about this organization, and with the good work they are doing with the charity and everything, it is very remarkable, and I feel blessed to be here. And if in anyhow, in any way, if you feel my help in any future endeavors for the students and for the benefit of them, I am heartily available for all of you for any time. Thank you so much.
Thank you so much, Jyoti
Thank
ma'am.
you so much, ma'am.
And I would like to express my gratitude and thanks to you, ma'am. And
My pleasure.
this is very important discussion we had today regarding the radiation safety and the consequences of these aspects. As you told about the uh, radiation awareness program, the patient and other laymen should also know about the hazard of radiation, because sometimes we have seen in the hospital the patients who doesn't know about the radiation effects, they also told if they have any pain, just go for the x-rays. Sir, we have pain here, can we go for the x-ray? So this is a humble submission to everyone: consult your doctor. Unnecessary radiation is very harmful, and how we can prevent all these things, as you very well said. And thank you so much, Jyoti ma'am, to keep out your precious time from your busy schedule. And I would like to request our dean ma'am, Dr. Shweta, for vote of the thanks.
Thank you, sir. On the conclusion of this national seminar, I would like to express my gratitude to the honored and skilled resource person of today's seminar, Ms. Jyoti ma'am and Dr. Ranjeet Singh. Thank you, sir and madam, for accepting our invitation. Your presence and contribution has made this national seminar a great success. I'm quite sure that the knowledge you share have benefited majority of participants and broadened their horizon regarding radiation and their consequences. Your thoughts have enlightened us, ma'am, and we propose similar event in future also. I extend my sincere thanks to the convener of this event, Dr. Nisha, co-convener Dr. Arsh, Dr. Mithu ma'am, Dr. Daljit ma'am, Dr. Shalu ma'am, for making this event successful. I don't have enough words to thank organizing secretary of the event, Mr. Rajdeep sir, and Dr. Harpreet Singh Cancer, who are working day in and out for making the event successful. Last but not the least, all the participants for being such a patient audience. Thank you, ma'am. Thank you so much.
Thank you so much, ma'am. And there is some important announcement to all participants. The Sant Baba Bhag Singh University will provide you the e-certificate for the same, and you will get all the certificates in email IDs by next 2 or 3 days by submission of your feedback form. Thank you so much, all of you, to attend this national seminar. Thank you.
Thank you, sir.
All participants, please switch on your cameras for a photograph, please.
Once all participants are requested to put on your cameras.
Okay.
Thanks to
you.
all. Have a nice time to all of you.
Thank you. Thank you to all.
Now, everyone can